Hello, calculus students. So we're moving on in Unit 1 to our third learning target. So we've had a learning target of limits, continuity, and now we're combining limits and asymptote as our third idea. So limits and asymptotes. And then side note, it's also featuring the intermediate value theorem. So these are the concepts that will be your next learning target. So we're starting off with lesson 7, which is connecting infinite limits and vertical asymptotes. Infinite limits and vertical asymptotes. Let's start with a warm-up. So per usual, give yourself about 5 minutes to try this warm-up problem on your own, and then return back here with me. Alright, so welcome back. Here's what I got for the warm-up. Problem 1 was just finding the points of discontinuity and stating the type of discontinuity. So both of these equations I had to put in factored form. In part A, when I factored the equation, I was able to cancel out or remove the term x plus 2. So I knew that was a removable discontinuity at x equals negative 2. And then x minus 2 cannot be removed or canceled out. So I knew there was an asymptote or an infinite discontinuity when x is equal to 2. In part B, you could do a lot of factoring. Nothing is able to be canceled out or removed. So both of the terms in the denominator will cause vertical asymptotes. So there are infinite discontinuities when x is equal to 6 and when x equals negative 1. And then the limit in number 2, if you just try to plug in 3, you get 3 over 0, which is undefined. Whenever you get something over 0, you have to check the limit from the left and the limit from the right, so that's what I did down there. And also when you get 3 over 0, you know there's an asymptote, so when the denominator is undefined but the numerator is not, there's an asymptote. And we need to determine, is the limit going to positive infinity, negative infinity, or if it's going to different directions from the left and the right, then it does not exist. So in this case, from the left and the right, both limits were going to positive infinity, which means that the limit overall also goes to positive infinity. All right. So this second problem especially is super relevant to what we are going to be talking about today, which is infinite limits. So an infinite limit is what happens when you take the limit as x approaches some value from the left or the right, and you get positive or negative infinity. So when you approach a value and the result is positive or negative infinity, then x equals a is a vertical asymptote. That's just what this is an infinite limit, okay? The limit is going to infinity. And I want you to note that it does specify it can be from the right or the left, which is just to say that we could have a graph that looks something like this. Oopsie daisies. And then at A, let's say there's an asymptote, and then only from the right is it approaching positive or negative infinity, and then from the left maybe there's like a hole there or something. So there are piecewise functions where there's a vertical asymptote, and then you only have the function reaching towards the vertical asymptote from one side or the other. This would be a special piecewise scenario, but I just want to note that it doesn't have to have the function coming from both sides to be a vertical asymptote. It just needs one side or the other. Okay. And this is pretty much it. So I just want to teach you about infinite limits, which also, it goes back to problem 2 here. So this is an example of an infinite limit, since the limit as x approaches 3 of x over the absolute value of x minus 3 equals positive infinity. This is an infinite limit. And basically what the result is, over here is that x equal a is a vertical asymptote. So that means in this case, what I would say from that theorem, therefore, x equals 3 is a vertical asymptote. Okay. We've kind of already talked about this idea before. We're just now giving you the proper definition of it, and we're going to look at more in-depth problems related to this. But this is kind of like the whole idea of what we're talking about today. Okay, so make sure you have this definition down. And then I do want to give you a small warning. So whenever we say that a limit equals infinity, technically that limit actually doesn't exist. And that's because infinity, this, is not a number. The word infinite literally just means without end. So infinity isn't a particular number, it's just to indicate that that number is getting big and it just keeps going. It's getting bigger and bigger and bigger. So infinity doesn't technically exist. But for simplicity's sake and to add clarity, instead of just saying the limit doesn't exist, it is okay to say the limit is going to positive or negative infinity, just because that gives you more information. I just want to be technical so that when you go into college you can understand this. This is more of a college idea. Whenever a limit is going to infinity, it technically does not exist. However, for the purpose of this class, it is totally okay to say stuff like this. You can say that the limit goes to positive or negative infinity, though technically it does not exist. Okay, let's do some examples. So example 1 says, find the vertical asymptotes of f of x. So very similar to the warm-up. Then using limits, describe the behavior of the function to the right and to the left of the asymptote. Okay. So in order to find a vertical asymptote, I need to find what will make the denominator equal to 0. That value is -1. So then I know x equals -1 is a vertical asymptote. And then I need to find the behavior to the left and the right of the asymptote. So I'll find the limit as x approaches 1 from the left of f of x. And I'll find the limit as x approaches 1 to the right of f of x. Okay. So this might be 0.9 squared minus 2 over 0.9 plus 1. So the numerator will be some positive, not positive, that'll be a negative number. And the denominator will be a positive number, so a negative over a positive is negative infinity. And then to the right of 1, we have 1.1 squared minus 2 over 1.1 plus 1. 1.1 squared is still a number that's less than 2, so anything smaller than 2 minus 2 will still be a negative number. And then the numerator is still positive, so that is also approaching negative infinity. So we have a vertical asymptote at -1, but to the left and to the right, it's approaching negative infinity. So I'm not exactly sure what this graph looks like, but if we had to sketch it, I know what's happening at -1 looks something like this. There's definitely more going on with the function that I don't know, but I know at this location, it looks something like that. Okay, so this is kind of giving us a better idea on how to visualize these functions. Okay, so examples 2 and 3 are going to be more strongly using like this definition and thinking logically about what this definition means. Okay, so example 2 and 3 will really be using the definition. So it says the function h is continuous at all x except for at x equals 8. if the limit as x approaches 8 from the right of h of x equals negative infinity, which of the following statements about h of x must be true? So this is kind of directly applying that definition. Oh no! This is directly applying that definition right here. So looking at your definition, if I know that the limit as x approaches 8 from the right of h of x equals negative infinity, what do I know about x equals 8? Using the definition, I know that x equals 8 is a vertical asymptote. Okay. The first one is automatically not true but if there's a vertical asymptote, we know that there's no value there. So if there's a vertical asymptote, it's undefined. And then down here, they're just trying to kind of trick you with the notation. So they talk about horizontal asymptote when you've got to be like, nah, this is a vertical asymptote, and I know that vertical asymptotes are an equation that uses x equals. So this one is correct. Okay. And then example 3, if the limit as x approaches 2 of g of x equals infinity, which of the following is a possible equation for g of x? So again, this is directly using the definition of an infinite limit. From this, I know that x equals 2 is a vertical asymptote. And so I have to think about what kind of equations have vertical asymptotes. Basically, I know there has to be a denominator, and that means x equals 2 is the value that will make the denominator equal to 0. So I can immediately cancel out a, because this is just literally a line, and lines don't have any vertical asymptotes. And now I guess we could just plug in 2. If I plug in 2 here, I get 1 over 4. That's okay. If I plug in 2 here, I get 1 over 0. So this is looking like the right answer. And here I get 4 over 3, which isn't a vertical asymptote. So C is our correct answer there. And that's it for this little lesson. Hopefully you are able to understand, the connection between infinite limits and vertical asymptotes and how you can find them in equations and blah 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 blah.